I work as a technical specialist for diffraction and analytical imaging. So what I want to talk to you about this afternoon is to look at why you need to look at particle size for inkjet ink, so why you might want to measure the particle size, and also to look at a couple of different technologies that we produce that you can use in order to measure that particle size. So we'll describe how those work and look at a few applications. So to give you an overview of my presentation, we'll start by looking at why particle size is important for inkjet inks. So we'll look at a couple of reasons why you need to measure the particle size. We'll then introduce two of the more common technologies that we use to measure particle size in a wide range of industries, including inkjet inks. So I'll tell you a little bit about how they work and what strengths they have in certain regions of analyzing inkjet inks. So we'll look at laser diffraction and dynamic light scattering. We'll then look at a few different case studies where these technologies have been applied to help understand the performance of inks and the processes that they go through. So look at tracking a milling process, detecting oversized particles in an ink, and looking at measurements at a high concentration. So I'm not going to tell you a lot about how inkjets work. That's what I've been learning over the past couple of days. But basically, we've got droplets being produced through an orifice, whether that's through a thermal or a piezo-generated droplet, pushed through an orifice in order to create that drop. So that's the first point at which the particle size becomes important, in that we don't want to have oversized particles or agglomerates that are going to block the orifice in an inkjet system. So that's one area we need to look at the particle size. We also want to control the particle size in order to control how good the pigment looks, so to control the optical properties of the pigment and the aesthetics of the coating that it produces. So we're talking about inks that have pigments in them, so insoluble solid pigment particles suspended in the ink to give us the slower UV degradation. They're going to be waterproof. And generally, we're looking for quite a small particle size. So it's usually around 200 nanometers, 200 to 300 nanometers. So the reason we want the small particle size is because that's where we get the best optical properties for our material. So this is a graph with our volume distribution against size for a good dispersion and a poor dispersion. So to get the optimum scattering from the pigment particles, we want to have a particle size around the 200 to 300 nanometer range. That's going to give us the best scattering, the best opacity from the pigment. If we've got bigger particles, so this is our poor dispersion, so we've got bigger particles, it's not as well dispersed, that's going to start to give us an effect on the film properties. So if we've got large particles, we might start to see a reduction in gloss on a coating. So we've got a more rough surface, we don't get as much reflection. And particles bigger than, say, 5 micron in size affect the stability of the dispersion. We're going to start to see surface imperfections on the coating. So that, in terms of the aesthetics of the coating, is why we might want to look at the particle size. And in order to control the production, we can monitor that by particle size as well. So we're producing them in a two-stage process. So the ink will be dispersed into a mobile phase. It will then be milled in order to remove agglomerated particles, and then to mill those primary particles down to the optimum size that we want at around 200 nanometers. So that's the second reason we might want to look at size, to control the optical properties of the pigment particles. And another reason we might want to look at the size and the particle size distribution is its effect that it can have on the suspension rheology. So the viscosity of a suspension of particles will depend on the size of the particles in that suspension. And in general, the smaller the particles, the greater the viscosity of the suspension. So the smaller your particles are, the more particle-to-particle interactions we have, and that's generally more pronounced at low shear rates where we're not disrupting those. So we've got a graph here with the viscosity against shear rate for an ink that's 750 nanometers and 175 nanometers, and that at low shear rate is going to have a higher viscosity. So we want to control the particle size to control that. We can also use the particle size distribution to control the suspension rheology. So for a given packing for a given volume density, so if you add a certain amount of material into the suspension, the width of the distribution will have an effect on the suspension rheology. So the broader the distribution, the greater the range of particle sizes you have, the lower the viscosity. So we can have a broad size distribution to reduce the viscosity. Basically, because it increases your maximum packing fraction, so the maximum amount of space you've got in the suspension for the particles to move around, and that will then reduce the viscosity. So here we've got viscosity against the volume fraction. So for a constant volume fraction, if we've got all the particles the same size, we get a higher viscosity. The more variation in particle size that we have, the lower the viscosity of the suspension. So that's the third reason you might be looking at particle size for controlling your ink performance. What we'll do next is look at the technologies that we use to measure particle size. And the first that we'll look at is laser diffraction. So both technologies we'll look at are light scattering based technologies. So in this case, what we're doing is looking at the angular scattering of light produced by a suspension of particles. So we've got, on this image, we'd have a series of particles suspended in a liquid perhaps, and we're aiming the laser at the center of the pattern here, and we get these bright rings in our diffraction pattern, and it's the position of these bright rings that we're interested in. We want to see where the peak in the intensity of the scattering pattern occurs. So the measurement that laser diffraction makes is to look at the intensity of scattered light as a function of the angle from that incident laser beam. So we basically take a slice out of that diffraction pattern and measure the intensity of scattered light as a function of angle. And that gives us particle size information on the basic principle that if we've got big particles, we get a lot of scattering at forward angles, so we get a lot of narrow angle scattering from large particles. So our example here of some large particles suspended in a cuvette illuminated by a laser, we get a bright ring very close to the center of the diffraction pattern. So that's our first scattering peak, and a bright intensity close to the center of the diffraction pattern at narrow angles. If we have small particles, conversely, they're going to scatter at much wider angles. So the scattering is now at large angle, and it's with much weaker intensity. So our example of a small particle scattering here, again, we've illuminated it in a cuvette, and we see that this is the much weaker scattering at wider angles. We don't get that bright peak close to the center. So that's the basic principle on which we get size information from measuring the angular scattering data. Is if we've got big particles, we get lots of narrow angle scattering. If we've got small particles, we get wide angle scattering with lower intensity. In order to interpret that scattering data from a particle, we use an optical model called Mie theory, which models the scattering from the surface of the particle, as well as light that gets transmitted and refracted through the particle. In order to model that scattered light accurately, we need to input some information about the material that we measure. So we put in a refractive index contrast. So we look at the difference between the refractive index of the particle and the refractive index of the dispersant in order to model that angle correctly. And that's where it can get a little bit tricky for pigments as they become multi-component systems, and it can be difficult to find that information out, but there are ways around that as well. We also make an estimate as to the absorption of the material to see how well we can model the light that's transmitted and refracted through the particle. So that's the model that we use to interpret the scattering data. Unfortunately, it works in the opposite way to the way that we would like. So it can take a size distribution and calculate what the diffraction pattern would look like for that size distribution. So we have to use it backwards in order to get from what we can measure. So we can measure a scattering pattern in the instrument. We make a guess at what the size distribution might look like. We then apply our optical model in order to generate a theoretical scattering pattern. And we can compare that theoretical scattering pattern to the one that we've measured in the instrument. And by looking at the differences between those two, between the measured and the theoretical data, we can adjust the size distribution until those two match as well as they can. We get the best fit between the two sets of data. And then what we report is the size distribution. So thankfully, when you're using one of these instruments, you don't see all of this going on, that goes on in the background. You don't have to look at it. What you will see at the end of the measurement is the size distribution, but also that final comparison between theory and measurement. And that's one of the ways that we make sure that our optical properties are accurately modeling the scattering data that we've measured. So that's how we get from scattering data to a size distribution. And the size distribution that we get from laser diffraction is based in terms of volume. So the technique is essentially measuring the volume of the particles that we're putting through. So our size distribution is based in terms of volume. Each band on that histogram tells us the percentage volume that's in that size class. And the typical numbers that we report are the percentiles of the distribution. I'm sure you've heard people referring to them over the past couple of days where you've gotten inks in with specifications on them. We tend to report the DV10, size below which there's 10% of the material, the D50, the median size, and the D90, it's the size below which there's 90% of the material. We also report averages. So we don't average by the number of particles because we don't count them, but we average according to the surface area, which will tell us about the fine particles as they're contributing much more surface area to the system, or according to the volume of the material. So we produce average values based on surface area and volume. And which parameter you use to specify your product depends on what you're trying to control. It tends to be milling processes and making sure there aren't any oversized particles. Look at the DV90 or the volume weighted average to tell you about the biggest material in your distribution. So that's what we get from laser diffraction. The other technique that we'll look at is dynamic light scattering, and that's based upon the Brownian motion of the particles. So in our video here, we've got some small particles here, and you can see these are being imaged through the scattering around the particles from a laser, which is one of our other technologies, the nanosite. But you can see those are moving around pretty quickly. We've got some large particles here around a micron, and they're moving around much more slowly. And it's by measuring that Brownian motion that we can get information on the particle size, looking at dynamic light scattering. How we go about doing that gets a little bit more complicated. So again, we're illuminating a cuvette with a suspension of particles in it. What we measure is the intensity of scattered light at a particular angle, and we look at how that intensity fluctuates with time. So the time-dependent fluctuations in the intensity give us what's called the translational diffusion coefficient. Basically tells us how quickly the particles are moving around. And from that, with the help of the temperature and the viscosity, we can work out what the hydrodynamic diameter of the particles are. So the diameter of a sphere that moves around in that liquid with the same size as your particle, plus surfactant, plus whatever's in there. So that lets us calculate the hydrodynamic diameter. If we look at an example of how that works for small and large particles, so those big and small particles we looked at before, our small particles move around really quickly. The intensity fluctuates very quickly with time. And in order to interpret that fluctuation, what we do is we correlate the signal, and we correlate the fluctuation in the signal against time with itself. So we look at how quickly that signal will break down, how quickly it starts to vary. And that gives us a correlation coefficient. So when the signal looks very similar to itself, we have a correlation of 1. When it looks very different, it goes down to 0. So the faster that decays, the smaller the particle size. And we apply algorithms to that decay in order to measure the size distribution. So conversely, our big particle moves around much more slowly. The intensity fluctuates more slowly, and it takes longer for that correlation coefficient to drop off. And what we get is a larger particle size distribution. So that's the basic principle on which we get size information, by looking at the Brownian motion of the particles. One of the advantages of using dynamic light scattering, and particularly on our system, is that we can decide what position in the cuvette we want to measure the sample, depending on the concentration of the sample, in order to optimize the signal. So this is a schematic of our setup. So the laser's coming in through a lens into the cuvette. This is where our particles are suspended, and we're measuring backscatter off at 173 degrees. And the system will choose what position in the cuvette it makes the measurement in order to, for small particles and dilute samples, in order to maximize the signal that we get relative to the noise. However, if we're looking at concentrated samples, we're going to adjust that position maybe closer to the wall in order to minimize multiple scattering effects. So all of these technologies tend to work on the principle that light gets scattered off one particle before it goes to the detector. So to make sure that happens for concentrated samples, we can measure much closer to the wall of the cuvette. Whereas for the dilute ones, we want to pass through more particles to get more data. So that's one of the advantages of dynamic light scattering, particularly for inks, is that it will let us measure at much higher concentrations. The results that we get from a dynamic light scattering measurement are a Z average diameter, so that's an intensity weighted average diameter for the system. It will also give you a polydispersity index, so an idea of how broad the distribution is. As well as that, it does a distribution analysis, so a more complex fit to that correlation coefficient decay to give us a particle size distribution. And that's a size distribution that's weighted by intensity. So that brings us to one of the more common questions we get about particle sizing, is that there's so many different ways of measuring it, and different ways of reporting the results, that people tend to get different results on the same sample, and the whole thing gets quite confusing. So what we'll quickly look at is the difference in the distributions that are reported by common particle sizing techniques. So dynamic light scattering gives you an intensity-based distribution. So this is a colloidal gold sample, actually, that we've measured by DLS. And that's, in this case, showing it to be bimodal. We've got some particles around 10 nanometers and some particles in the hundreds of nanometers. So the distribution is weighted by intensity, and intensity is related to the diameter of the particle to the power 6. So it has a huge effect if we have any big particles, because they contribute so much to the intensity distribution. It makes dynamic light scattering a very good way of detecting small amounts of agglomerates. And similarly for laser diffraction, what we report is a volume-based distribution. So we're now looking at diameter to the power 3. So if we take the same sample, same measurement, and transform it into a volume distribution, we've then still got some peak from the large particles or agglomerates, but 90% of the material is now around 10 nanometer. Finally, if you were to look at this sample by microscopy, and that's where this example came from, somebody had measured the gold nanoparticles by TEM, and they come up as TEM by all being 10 nanometers in size. And we measured them by DLS, and they were mainly in the hundreds of nanometers by size, so it's a bit confusing. And here, each of those particles is going to contribute equally to the number distribution. We're counting them, so we get equal contribution whatever the size. And it may only be one or two large particles that's causing that intensity peak, so they don't become significant in the number distribution. So if you get particle size results, it's very important to find out how they've been measured and what they're reporting in terms of the distribution that they're producing. In terms of a summary of these two techniques and their applicability, so laser diffraction lets us measure to below 100 nanometers in size and up to above 2 millimeters in size. So it has a huge measurement range in terms of size, which makes it very widely applicable in a huge range of different applications. So it makes it ideal for polydispersed materials, and we'll see later about following milling processes. We can measure dry powders, suspensions, emulsions, and sprays, and we can follow dispersion processes. So we can add samples to a unit, and we can change the dispersion conditions and look at how we can disperse a material. In terms of dynamic light scattering, we go from below a nanometer up to around 1 micron to 10 micron. What limits dynamic light scattering at the top end is when the particles start to settle. So they start to fall out of suspension. So it will depend on the density of the material at what point we no longer get useful data from dynamic light scattering. It has a very wide concentration range. So because we can automatically set the position, we can measure from 0.1 parts per million up to 40% weight volume, depending on the sample. It has very minimal sample prep, and it's non-invasive. So you can put your sample in the cuvette. You can then take it out and do other things with it if you need to. Both measurement techniques are very reproducible, very repeatable. They're also very quick, and both have ISO standards which cover how the instruments work and what you can expect in terms of the performance of these instruments. So the next bit we'll look at is a couple of case studies on both the Mastersizer and the Zetasizer. So looking at wet mill monitoring, detecting oversized particles, and how we can measure at high concentration. So in this case, we're looking at a pigment that's being milled over time. So we're looking at the cumulative distribution, so the percentage below each size against particle size, starting with the premix. So we've got particles here that are below 100 nanometers, up to 100 micron in the same sample. So we can quickly characterize that. As soon as we start milling, we're looking at the decrease in particle size. So we're removing all these large agglomerates. And as we mill it over time, we can follow the process of the particle size reducing with time. So that shows you the whole size distribution in that case. What we can then do is extract the percentiles from that in order to track that milling process. So here we're plotting the 10th, 50th, and 90th percentiles of the distribution against time. So what we can see in terms of the milling process is that we get the most substantial decrease in particle size initially. So we're breaking up some of the agglomerated particles. We're starting to mill down the primary particles. So we see the most significant decrease in particle size right at the beginning. And then we're looking at a gradual decrease in the DV90. So those are the largest particles in the distribution being gradually reduced in size as we mill them further and further. So this is how you can use diffraction in an ink system to look at the milling process, to look at what point you have to stop. So making sure you don't put more energy into it than you need to in order to mill down the pigments. So if you wanted everything below a micron, you could have stopped after maybe an hour and 20 minutes. If we want to get everything down to below half a micron, it's about 3 hours of milling now. So the wide range of laser diffraction lets you follow those processes. In terms of looking at ink stability, the ability to detect small amounts of agglomerates quite quickly is useful. So here, what we've done is we've taken a good dispersion to start with, and what we're doing is we're going to seed in some coarse particles and then seed them in a known volume so we can tell at what point we start to detect those oversized particles. So this is our primary sample in green. We've then got the seed material, which has got some agglomerates here at around a micron. And we're then going to add certain percentages of those oversized particles. So at 2% seed, you can see in grey, we've just seen a peak of material appearing at about 1 micron. So what we've done in this case is to add different proportions of that seed material to look at how well we're picking up those agglomerates. So from 0.4% seed material up to 2%, which was what the example we showed on the previous page. And we're plotting the DV99 against the amount of seed material added. So that parameter is going to be very sensitive to small amounts of oversized particles. So we can clearly detect small amounts of agglomerates, which would let you find out that the ink's not stable or it's not well enough milled very quickly. So the example that we'll look at from the Zetasizer from dynamic light scattering is looking at blue pigment dispersions. So in general, to do any particle sizing, we have to significantly dilute the sample, and that can cause problems in terms of we don't really know what that does to the sample, how much it changes the sample from its initial concentration to the concentration at which we need to measure it. So being able to measure it at its original concentration or as close to it as possible is what we want to do. And here we've got a blue pigment sample that was at 15% weight volume, and we've taken samples from a bead mill over 1 hour intervals, and measurements were made at sample concentrations of 1.5% weight volume, so we've diluted it a little bit in order to eliminate the particle-to-particle interactions. So we need to get rid of those so that it's pure Brownian motion that we're looking at, and then measured on the Zetasizer Nano at 25 degrees C. So if we look at that dispersion process, that milling process, on the right-hand side, what we start with are the neat, that's the neat ink concentration, so that's sample A. The concentration at which we measured it, which is 1.5% weight volume, and the concentration at which you would have to measure it on a typical 90-degree dynamic light scattering system. So that's detecting it, diluting it about 10,000-fold. So the slide I showed earlier where the light's coming back off and we're measuring it at 173 degrees is what allows us to measure at these higher concentrations. Where you're having to go through a significant volume of the sample, we'd have too much multiple scattering, so we have to measure at lower concentrations. So these are the measurements that we've made over different milling times. So we start off with some particles around the 20, I can't quite read that one, just over 100 nanometers, and then we've got some big particles in there as well. So that's primary particles and some agglomerates is what we start with at the beginning of the milling run. So as we mill it, similar to what we saw in diffraction, most of the change in the sample occurs right at the beginning. We're starting to disperse and mill the particles down in size. We did get a slightly odd result after 3 hours where it didn't look much different, but that measurement was repeated. It was reproducible. They even repeated it at lower concentrations to make sure there wasn't any effect there. So what we end up with now is the primary particle size down at around 150 nanometers. We've also reduced the bottom end of the distribution from 60 nanometers down to about 45. So that brings me to the conclusions for this presentation. So in terms of the two techniques that I've talked about, the wide range of laser diffraction allows us to do things like following milling processes from the premix to the final particle size, characterize that final particle size and easily detect agglomerates in a pigment dispersion. And dynamic light scattering adds on the benefit that we can measure at much higher concentration, so we can look at what effect diluting the sample has on our material. And the combination of these two techniques give us a very thorough way to be able to characterize the particle size of inkjet inks. So that brings me to the end of the presentation. If anybody's got any questions?
Thank you very much, Anne. Is there anybody in the office and the audience that has questions?
It's a curiosity. If you can go back one in the slide, typical DLS patterns, you have a clear signal. And my curiosity is the degree of confidence you have in that distribution, because all these signals are Gaussian, that are not so common in particle size distribution, no? So no doubt about the maximum, but which is the confidence on the width of these bands?
Yeah, so that comes back to the two different analyses that are performed on the correlation function that dynamic light scattering uses to get the size information. Primarily, we can get an average size, a Z average size, and an indication as to the polydispersity. But then the second part is looking at that decay in the correlation function and applying a multi-component fit to that correlation to produce the size distribution. In terms of the absolute accuracy of the technique, I don't have the number on the top of my head, but the combination of those two analyses gives good confidence in the results that we get from dynamic light scattering.
Yes, you mentioned that the techniques measuring effectively the hydrodynamic radius. Do you notice much of an influence if you go from a low molecular weight dispersing material to a high molecular weight polymeric dispersing material?
So is that what you're dispersing it into?
What you're using to stabilize the pigment?
Or attaching to the particle to stabilize? Yeah, so it would have an effect of that. So it's basically the diameter of the pigment particle plus the surfactant, because that will affect how it moves in the dispersion. So if you're attaching things to the surface, they'll play a part.
I was more considering, say you use a acrylic polymer with 100,000 molecular weight, for example, what sort of effect that would have in terms of the hydrodynamic radius when it's being used to disperse a pigment?
Might be going slightly outside my area of expertise here, so I'm not sure how to answer that one for you, but I can get one of my colleagues to give you an answer looking at that. Yeah. Sorry.